usually after either two things. One, explicitly characterizing a complicated or very high-dimensional probability distribution, or more commonly, not being able to explicitly characterize it, but being able to sample from it. So in the case of diffusion that you may be familiar with, this would be some kind of conditional sampling algorithm. So you have a model where you give it some text, and non-deterministically, it gives you back, say, an image describing that text. Make sense? Okay. So our example for now is going to be an unconditional model. So instead of giving our model text and it giving us back an image describing that text, we're just going to have a single model that samples from one probability distribution unconditionally. So we want to model very complex and high-dimensional probability distribution of, say, cat images. For now, you can think of that as just a fixed, maybe 512 by 512 image. Okay, so who knows what diffusion is from physics? Anyone familiar with it? Okay, well, it's on the slide here. I wrote diffusion's the net movement of something from an area of high concentration to low concentration, which you can see here. There's a simple example of food coloring. And this diffusion process typically happens over a long period of time. So when you just drop food coloring in water at the start, the very instant you dropped it in, you're not going to expect your water to be completely red, but you're going to expect high concentrations of your food coloring in certain parts of your water. But if you come back maybe a day later, you might expect red water, right? And an important keyword here is equilibrium, which refers to equal or approximately equal concentrations. So you no longer have movement of something from high concentration to low concentration, but the concentration of, well, something is balanced throughout the entire system that you're dealing with. This is up to some kind of movement, of course, of maybe molecules. Its concentration then stays approximately equal. Okay. So now we're going to take inspiration from this physical process and try to design a diffusion process for images. And what that's going to look like is we're going to define our equilibrium as the image looking like it's sampled from a normal distribution. So you can imagine for our 512 by 512 image, imagine we sample each pixel independently from a normal distribution. So just standard Gaussian with mean 0 and standard deviation 1, right? And what we're going to want to do is define a process to go from our regular images of cats slowly to an image that looks like it was sampled from a normal distribution, or is approximately in equilibrium. This kind of makes sense? Yeah.
What does it mean to sample a pixel from a normal distribution? Are you sampling the color of the pixel?
Yeah, so you would take an image, you would define some way to normalize this image.
Okay.
Then you would sample from a normal distribution, and then you would unnormalize the image.
Okay.
Yeah. Make sense? So how we're going to do this, I want a simple algorithm to do this, is first we need to discretize the process. So unlike diffusion in physics, where you would usually treat this as random walk according to some kind of stochastic differential equation, we're actually just going to chop it up into, say, 1,000 different time steps or something like this to inevitably be able to program this, right? You can imagine this is the same thing as taking a video of our food coloring, dropping in the water, because what's discretizing it is your frame rate. Make sense? Okay. Here's an example of what that process is going to look like. So we're going to start with our image of our cat, and we're going to slowly approach noise. And there's only 1, 2, 3, 4, 5, 6, 7 steps here. In practice, we're going to use many more. Okay. So how do we go about doing this? We go about doing this with a distribution we call Q, because remember, we want to treat this as a sampling or non-deterministic problem. So we don't have these deterministic mappings from one thing to another. We just have a mapping where we're slowly adding noise to an image. Make sense? Okay, so one interesting way we can do this is via normal distribution. Now, it might be a bit scary because it's multivariate normal, which can be kind of annoying sometimes, but it's actually exactly the same if it's just a single pixel. So if you're trying to visualize it, just visualize it pixel by pixel. Yeah.
You can explain why is it non-deterministic?
Oh, well, we want to treat this noise process in a non-deterministic way. We don't want this to be a deterministic single mapping to our equilibrium. We want to treat this as a random process, like we do in physics as well. This will become more clear once you see the algorithm of how we actually generate these images. Yeah, but I can get that there's some confusion for now. So one interesting...
Just a small introduction. Feel free to take these at any time.
Yep. So one interesting way to do this is the normal distribution here, where we want to keep these beta terms, or called their variance schedule, sometimes called a beta schedule, close to 1, so that this mean term right here is very close to our image throughout the forward process. And we're going to slowly add some noise, which has very small variance, because remember, we want to keep our betas very close to 0. And these hyperparameters are contingent on what you're using the problem for. If you want to come up with some kind of sampling problem that doesn't have anything to do with images, the hyperparameters used in the paper that we're presenting today might not work exactly. The best way to do this is to just, like we said on the screen, have our diffusion algorithm define a way to do this, and then just visualize to see, is this reasonable enough? Okay. Well, like I said, like the last slide, there's no best or correct way to do this. There's just a few ways that work reasonably well. And this is a common paradigm in machine learning. Things that work reasonably well are usually Gaussian. We know a lot of things about them. They're tractable. We have analytic expressions dealing with them from statistics. And if it can be Gaussian, why not? It makes things easier later on. Okay, so like I also said before, we want to keep our beta terms very close to 0 so that this process is very, very gradual and a better approximation to a continuous random walk instead of a discrete one. And we're also going to set t equals 1,000 time steps. We'll use t to denote the number of time steps throughout the rest of the presentation. So instead of, again, having 7 images here going closer to noise, we're actually going to have a chain of 1,000 of them. Make sense? Okay, so here's our diffusion algorithm now. Oh, I forgot. One more thing you can do is, because we're just defining beta 1 and beta t, well, what about all the betas in between? Again, you can do this in several different ways. So you can scale them quadratically, you can scale them linearly. I just scaled them linearly for the purposes of this presentation. You can see if you're familiar with NumPy, I just use linspace to be able to do this, which even if you're not familiar, it should make quite a bit of sense. Yeah. So why don't you all take a minute to read through this diffusion algorithm on your own and see if it kind of makes sense or aligns with what I've talked about so far. See if you have any questions about it. Yeah.
Is that how you generate training images, or not quite understanding?
The understanding will come after this. What we're trying to do now is just replicate what's going on in our physical process. So trying to come up with a way to, an algorithm to replicate what's going on with our water and food coloring for images. It'll become clear how this relates to our original problem over the next few slides. Yeah.
Every time you do sample,
Yep. Yep. Slowly over time. So just a tiny bit of noise over a large number of time steps. Make sense? Okay. So now what we want to do is train a model to replicate the reverse process. So currently what we're doing is we have an algorithm that goes from here to here. And the question we want to ask is, can we create a distribution where we can just sample normal distribution, an image from a normal distribution, and be able to reverse this process and sample our image at time t-1 given our image at time t. Does this make sense to everyone? How if we could solve this problem, we have a generative model. Yeah? Okay, cool. So what we can do is we can actually just apply Bayes' rule. So if you remember before, you'll see all these terms for Q here are something that we're familiar with, and an algorithm that we know is Gaussian in certain cases right here. Everyone familiar with Bayes' rule for generative modeling? Okay, any questions about this so far? It comes from here. This is a better explanation. It comes from this exact formula right here. Do you want me to write it on the board so you can compare with the presentation? No?
I had it.
Oh, okay, yeah. So you'll see here, it's exactly the same kind of formula. Where we're not actually moving around x naught, we're still conditioning on it regardless. Make sense? Okay. Oh, yeah, okay, perfect. So this term is called likelihood. This term is called a prior. This term you can think of as just a normalization constant. So this term we know, it's defined in our algorithm. So we know this term is Gaussian. Okay, everyone agrees? Now, we have a bit more math to see why our prior is Gaussian. So here's an interesting, well-known fact, is if we want to sample x according to normal distribution, or sorry, just a Gaussian distribution with mu and standard deviation sigma, does anyone know how, let's say we have an algorithm in our computer where instead we can sample a noise vector epsilon with mean 1 and standard deviation 1. Does anyone know how to create a sampling algorithm for x from epsilon? Well, the way we can actually do it is just write x is equal to, I think, mean plus epsilon sigma. It's the same as sampling x from this normal distribution here. Okay. Now, in order to show that our prior is Gaussian, we apply this several times up to t times, actually, right? So we're going to apply this same trick. It's called a reparameterization trick. If you've ever taken a deep learning course with VAEs, this might ring a bell. And we do this some number of times. If you want to be very rigorous, this is a linear recurrence you get from applying this t number of times. And there's well-known ways you can go on Wikipedia and see there's closed forms in order to solve this. But the interesting part is that we get is it's actually Gaussian. Any questions? It's kind of tricky.
The first t was 1,000, or sorry, the step sizes you had 1,000,
The total number of steps is 1,000.
but this t can be arbitrary.
This t is arbitrary, so it's natural numbers between 0 and t or 0 and 1,000. Yeah, there's might be actually in my presentation some small index errors. Maybe there's little off by 1 errors at some point, but that doesn't really matter for the sake of what I'm trying to explain, right? Does everyone follow that this is Gaussian? Yeah.
I don't know if you kind of mentioned this before you expect us to understand it, but why do we care whether the whole term is Gaussian or not?
I will get to that. That's in my next slide. This presentation's tricky because you have to care a lot about seemingly useless things that I tell you, and then later on you'll see why they're really important. I tried to do it backwards originally, but I think it's actually harder to understand. This is nice because I'll post these online, and then you can read it, understanding all the context. And
it just that first 1,000, that's just practical workable limit.
Yeah, so ideally, to represent something continuous, we would take t as it approaches infinity, because then we get something that's approximately continuous that represents our physical process. In this case, we just take t equals 1,000 to add noise to our image slowly. Yeah, that's just one way of doing that. Okay, so what's very important from this is after applying Bayes' rule, we get that our prior is Gaussian and our likelihood is Gaussian. So why is this important? Well, it actually means that our reverse distribution itself is Gaussian. So if you have a Gaussian likelihood, if you have a Gaussian prior, you'll get a Gaussian what we call posterior, which is this distribution right here. There's some tricky algebra that goes into this, and you can work it out on your own. Again, I didn't want to work it out to bog you down in this presentation, but just take my word for it. That's why we care about those two things being Gaussian. Make sense? Any questions? Okay. I also said that you can explicitly see this, and it's gross. One thing you'll notice here are we have some constants in this term here that depend on x of t and x naught. See, we have other terms like this -1/2 term, this exponential term, and you'll see on this side here, actually, if we just exponentiate both sides, you can see that you get something similar. So there's multiple ways to do this. This is the nicer way if you just know that a Gaussian likelihood and a Gaussian prior gives you a Gaussian posterior. You don't have to go through any of this, but you can if you really want to. I don't judge. Okay, so what does this mean? This is very, very important because now we know what. What functional form does our reverse distribution take on? Does anyone know? This is what we applied Bayes' rule for originally, is to write the reverse distribution in terms of the forward one. So we know that our likelihood term and our prior is Gaussian, which means what? That this is Gaussian. So our reverse distribution is Gaussian. Okay, cool. Now, why is this nice? Because we can turn and formulate our problem into a learning algorithm, where instead of coming up with some crummy algorithm using all of this algebra to get an expression for our mean, an expression for our covariance matrix, we're actually just going to have a neural network parameterize both of these things and come up with an algorithm to learn this distribution. Make sense? You can see knowing that it's normal is quite nice because it, it shrinks down our search space. And as you'll see later on, it actually leads to a convex loss function, which, again, for those of you very familiar with machine learning, is the holy grail. Yeah? Okay. Any questions?
Wait, so how many parameters are there? Just two? Like just the mean and
The parameters to the normal distribution, there will only be two of them. Of course, if you have an n by n image, there will be much more than just two of them. But again, in the simple case, to appeal to your intuition, you can just think of it as a single pixel in which there are only two. There's much more parameters in our model, however. We could use a very large machine learning model or a large neural network to parameterize both our mean and our covariance matrix.
but the final parameters are just two for every pixel.
Yep, sure. Not exactly, because when you have a covariance matrix, this gets bigger, but you can think of it that way. Sorry, any other questions?
This is just a little bit, is the primary advantage of the Bayesian model in there to guide the training, or is it acting as the sort of nonlinearity when it's setting the weights and things like that?
It's
a little bit
it's
both.
A way to solve our problem. It's this is what's tricky with machine learning. Is usually
can work. It's if you get the parameters right, it will solve it because it's just the reverse.
So that's what we're going to focus on right now. So this seems like what we've gotten to so far seems like a reasonable problem to solve. Instead of solving for some or trying to sample from some unknown distribution, which seems kind of tricky. How do you characterize all possible probability distributions in existence? I don't know the answer to this question, but we know how to characterize Gaussian ones. So it makes our learning problem easier. And you'll see later on, because it's Gaussian, it makes it
So you're
easier.
solving for each potential arbitrary step of that's the
Yeah,
idea.
so the idea is just this. We want to sample an image for time step t minus 1 from a distribution q, x of t minus 1, given x of t. So given x of t, we want to have a distribution q of which we can sample t minus 1. Then what do? We sample t minus 2, and then t minus 3, and then t minus 4. So if we sample our original x big T from normal distribution, and we apply this in our algorithm t times, or in our case, or the example of the paper, 1,000 times, what do we get back? We get back x0, which, if we've done things properly and we've come up with a reasonable algorithm, is our image. Do you guys understand? Right. So you see, this is why it's a generative model, because this is sampling. This is not a deterministic algorithm. So if I give this algorithm x of t and I ask for x of t minus 1, this is a random process. So another nice thing about this generative model is ideally it should give us a wide range of different cat images, or it should encompass the entire distribution of possible cat images, so long as we give it a reasonable enough amount of data. Make sense?
Just on one,
Yeah.
I don't want to sidetrack.
No.
What, before this paper, because I know Bayesian models were always suggested, like, how can they work?
Yeah.
There were generative models. How did they, there was other ways to sort of, like, they were just very random guesses, sort of like that.
Yeah, so generative model refers to just a model that's not deterministic, where you want to create a distribution either explicitly to work with it, or in our case, not explicitly, but learned by a neural network and being able to sample from it. So you're right, there's a lot of different generative models. This is just one of them. And it turns out in practice, it's worked very, very well for a lot of different problems. And you can see we have a lot of intuitive control over what we're working with. So with other generative models, you might not have this kind of control. Like the forward process we designed with those hyperparameters, I can just write an algorithm to animate this forward process for me on my computer and just check as a human to see, is this reasonable enough? Is this close enough to our physical intuition from diffusion of the food coloring in the water? Again, the answer to your question is just, it's a way to do it. Yeah, this comes up a lot. So. Any other questions? Okay.
So,
yeah.
instead of just adding Gaussian noise,
Yeah.
now we're adding, we're applying Bayes rule and then adding.
We apply Bayes' rule to go in the opposite direction. So our forward distribution is adding Gaussian noise to something, which is x of t given x of t minus 1. We apply Bayes' rule to see that our reverse distribution is Gaussian. And now we want to design a learning algorithm to parameterize the mean and the covariance matrix of this Gaussian distribution. Yeah.
I remember you mentioned earlier about the covariance matrix. Could you briefly explain what a covariance matrix is?
No, I don't want to. What time is it? Yeah, we need to pick up the pace a bit and get through this presentation. So I can talk to you about it after. Yeah, that's all.
Is this tractable, or do we have to use something like Hale divergence?
Yes, that's what's on the next slide. Great job. This is not tractable. Thanks for bringing that up. You might ask, well, if this is our distribution, we're done. We can just sample from this. That's an integral, which is annoying and hard to evaluate, and we can't do that. This happens for most Bayesian generative models. So we'll see. The trade-off to using different tools to be able to do this will be that we can no longer have an explicit formula for our distribution. What we instead have is just a distribution that we can sample from. An explicit formula, in a way, we can have it with maybe 1 billion parameters in some large diffusion model or something, but that's not practical, so don't care to really call it explicit. Okay, so that's exactly what we're going to do next, is use KL divergence. You can use a lot of different things, but I thought KL divergence is simple enough for this lecture. Okay, you guys should be able to understand. Okay, this is Claude Shannon. He's called the father of information theory. He's a cool guy. So now you can see our problem turns into how do we quantify a notion of distance or similarity between two probability distributions. So you can see here, maybe we want to call our distribution maybe p theta is this normal distribution mu of theta and sigma of theta. And we have our true reverse distribution as p. And we want to minimize the notion of similarity or distance between these two. And that's going to be our big training objective. Everyone confident on the training objective? Okay, cool. The way we do this is, it's called by computing the expected value of an information function. We're going to see what that means on the next slide. So now we're going to talk about what an information function means, or what it is. And intuitively, what an information function is it tells you the information that you get from some event occurring when you observe it, when it's sampled from a probability distribution. And we're going to say that an event has high information if it's very unlikely, and an event has low information if it's very likely. This is a tricky idea to grasp at first, but any questions on this? It's something that you'll have to come back to. Okay, so how are we going to do this? If something has high information, if it's very unlikely, low information, if it's very likely, if we have an information function that takes values in probability, then it's going to be a monotonically decreasing function, or just simpler terms, a strictly decreasing function. Okay, another thing we're going to do is we're going to specify that information function evaluated at 1 is 0. So in other words, an event that is guaranteed to occur tells us nothing new or gives us no new information. One other thing we're going to do is we're going to say that if we have two independent events, we want the information of both of those independent events occurring to be the sum of the information of them occurring separately. Do these seem reasonable to everyone? Again, it's tricky to grasp at first, but I need to get through the slides a bit quicker. Okay. So it turns out what we can do with this is we can make one more assumption and get and get some kind of form to our information function. So typically what we do in statistics or machine learning is assume something is twice continuously differentiable or infinitely differentiable because it allows us to do calculus with it and make very relaxed, easy assumptions. This is common in stuff like the definition of variance. You may have wondered, why is variance squared distance between sum of squared distance between points instead of absolute value? Answer is just differentiability. You want to be able to have something that's easily differentiable in scenarios. So we make that assumption here as well. And it turns out with this, you can use this third property right here and take a mixed partial derivative. So it's be just a partial derivative in P1 and P2 of both sides. You can make a substitution U equals P1, P2, and you get an ordinary differential equation just in terms of U that you can solve with your assumptions on the previous slide. So those of you that are familiar have taken a differential equations course. This is also referred to as an initial condition. For those of you who aren't familiar, when we solve this differential equation, you can think of this in terms of mean value theorem in calculus. So we have an integral of something equals an integral of something plus c, and by specifying I of 1 equals 0, this goes to 0, and we get something nicer without a lot of parameters in it. Okay. So it turns out if we do this, and we also apply our monotonically decreasing assumption, we actually get that the information function takes on this form, which is 1 over log base b of p for some base b, which is also just negative log base b of p. Here we can think of, sorry, I'll go on to the next slide. Here we can think of b as a unit of measurement for information. So if this is a natural logarithm, so it has base e, I think they're called nats. It's a decent name, I guess. Base 2, they're called bits or Shannons, because I think that's what Shannon originally used in his paper in the early 50s. Okay, so now we have notion of a function that is able to quantify, given the probability of some event occurring, how much information does this give us or tell us when it does occur. Okay, it's tricky, again, just come back to it. So now what we can do is we can define a quantity called entropy, which is really just I of p is our information function. Given a probability distribution p, we just say entropy of x. So x is a random variable that is sampled from p. We just define this as the expected value of our information function. This should be pretty intuitive for all of you. You just say the expected information from some probability distribution. To give you some more intuition, just using intuition alone and not some of the math on the slide, can anyone guess maybe a distribution with very low entropy, or doesn't tell you a lot of information?
Would it be a uniform distribution?
Yes, exactly. That is the lowest, just a uniform distribution. Can anyone give me an example of a distribution with higher entropy? Well, you can, any other distribution, because I said this is the lowest. So you can think of as a normal distribution like this or something. Cool. Kind of making a little bit of sense. Okay, nice. All right, now we're going to define, it's tricky, but we have to do it for our model. We're going to define a function called cross entropy, where entropy is an expected value p, or information function of p. We're going to define cross entropy as if it's taking on values in Q. And instead of building towards this, like we built towards our definition of entropy, we're just going to define this, and it's easier to analyze and see some properties about it and see why it makes sense as a definition. So one, we can show that our cross entropy is bounded below by entropy in P. The entropy of P, of course, is just our entropy in P, because you just replace this with P, and it's the same as this. Okay, and the more general, very nice result has to do with these things called exponential families. So there's a very broad characterization of a lot of different probability distributions called exponential families. And what's very nice about them and why we study them and why we care about them is because they make things convex. Yeah, so quantities like entropy or quantities like cross entropy will be convex functions. And anyone know why we might care about them being convex?
Does it allow you to solve for a minimum?
Yes.
Some minimum?
Yes, it allows us to guarantee that if we use gradient descent to train our machine learning model, we will reach our global minimum.
Okay, good global. minimum.
Yes.
So not a local minimum.
No,
Okay.
because it's a convex function.
Okay.
Something like that. There is only one local or global minimum. It is also a local minimum if you just look at it locally. Okay. So what's very interesting is using this property right here, we can actually take a difference between cross entropy and entropy, and we can see that if we minimize, or if we, again, think of Q instead as P theta from before, if we minimize the difference between entropy and cross entropy, this will give us a distribution P theta that well approximates P. And the reason it will do that is because we minimize it using a convex loss function. Okay? All right. So my friend said before, this is called KL divergence. And something that's tricky with KL divergence is that it's actually asymmetric. So KL of PQ is actually not the same as KLQP, but if you verify this experimentally, you can see that if we know that, well, again, what is our reverse distribution? What functional form does it take on?
Yes.
Gaussian, right. So if we know that P is Gaussian and P theta is Gaussian, it turns out this doesn't matter, and it's actually nice. So depending on how you minimize KL divergence is if you take P or Q first, or Q or P first, one of them is called a moment projection. So it'll accurately preserve the moments of this underlying distribution with a Gaussian approximation. The other one is called an information projection, where it will actually, as we minimize it, will decide to latch on to a single hump of this distribution or something. But because this is a convex loss space, and because we're dealing with two distributions of the same functional form, what actually happens is we just have a Gaussian, and we approximate with a Gaussian. So you can see using both approaches before, they work in a similar way. Okay, cool. Any questions?
Just out of curiosity, what did the letters KL stand for?
Kugler, Kobach-Leibler, Kobach-Leibler divergence.
So it's just the author's initial.
Yeah.
Okay.
The two authors.
Two authors.
Yeah.
Cool.
Yeah. Okay, so instead of using KL divergence, what we sometimes use is we swap the terms in KL divergence, which we can do because something's truly Gaussian, and we minimize what's called a variational lower bound on this distribution. I'm not going to go into that. It's something that, again, is a little bit tricky and takes some time to learn. If you're curious about learning it, look up something called elbow. This is very common. There will be a lot of good literature, simple introductions to it, and it'll give you a better idea of what's going on here. But what happens most of the time with these generative models, especially at the time, so a few years ago when a lot of people were still using KL divergence, is you have some expression for log likelihood, you have some expression for KL divergence, and you try to minimize and maximize variational lower or upper bound on these kinds of terms. Okay, so this begs the question, is this still the case? And do we still use KL divergence in our models? Well, no, not entirely. I guess before I move on, I should talk about, is everyone clear how we've completed our problem? So our training objective is to minimize KL divergence. It seems pretty simple. I know there's some machinery behind it, but if you just state it that way, is anyone confused about how we've solved this problem? It's a convex loss function. We have a nice functional form to describe it. And if we just minimize this using gradient descent, we're done. And we've created a way to sample from our images of cats. Yeah?
So usually we use positive
So this is what's really interesting is you might have seen, I don't want to talk about this for too long, but if you've done logistic regression before, you've probably seen cross-entropy loss or multi-class classification. What's actually interesting is you're really just minimizing KL divergence there. what you're doing is you're just assuming that your other probability distribution stays fixed over time. So if I train a model today that talks about the weather, if I wake up tomorrow, I'm just going to assume that I can use the same model. This might not be true, but we just make this assumption. So in those cases, when you're minimizing cross entropy loss, you're actually just minimizing KL divergence. It's just your entropy term is constant. So if you're minimizing constant plus some other term, what do? That constant just goes away, and you're left with constant entropy loss. So it's cool you made that connection. Nice. Okay, so now we're going to move on to the actual sampling algorithm of the paper called DDPM. And this is going to be much, much easier. So can anyone recap our training objective from before? I don't mean explain how we get to it, but just state what it is. What are we minimizing from before? KL divergence between what?
Distribution of cats and distribution of random ones.
Yeah, exactly. So we have some p theta, which we parameterize as a Gaussian. We have some p, and we just want to minimize the KL divergence between the two. Yeah? Okay. Now what we're going to do is we're going to rethink this model. And instead of minimizing KL divergence, we're actually just going to use mean squared error to minimize the difference in noise between these two things. So before we had a neural network, or maybe two different neural networks that parameterize our Gaussian distribution, right? Yeah? Now what we're going to do is we're going to have no parameterization. And I'm going to say, I'm going to train a neural network that predicts that given a noisy image and some other information like the time step, I'm going to predict back the noise. So now we add some true noise epsilon to our image, and we want to approximate this using some quantity epsilon theta, where these are, say, like the parameters of our neural network, something like this. Make sense? Any questions on this? Again, this is very nice because mean squared error, what is it? It's a convex loss function, so it's pretty good. We're able to do this. And it turns out that instead of dealing with distributions p theta and p, it's actually nicer in practice to predict and approximate the noise we add to an image with some neural network epsilon theta. Any questions about this? So our problem is changed from minimizing these two distributions to having a neural network that predicts the noise we add to an image and minimizing the mean squared error between the noise we actually added to it and the noise our network predicts. Any questions? Okay. Well, if we solve this, yeah.
Wait, so where did the KL divergence go again? You just converted it into EMS.
It was a different formulation of the problem. But I thought it's important, and I left it in this presentation, because it'll come up in lots of different ways when you're using these models. It's actually still very, very important. Because this is an introduction, it seems like we just forgot about it and we're moving on to something better. But I introduced them two different ways to do this because they're both quite important to be able to go use these models and understand them. Yeah.
And it's assuming noise applied in a similar procedure or the same procedure.
The exact same procedure. You'll see here, these terms are similar. These are not betas from before. This alpha bar is actually, if we go back quite a bit, you can see when we used our reparameterization trick from before, they're defined here. They're just notational shortcuts because algebraically this thing can kind of get long and gross. And you don't want to type this out every time with a 1 minus beta t term. You just call it alpha t bar. It's just for the sake of doing algebra, but yeah, our forward process again is exactly the same as before. We're just coming up with a different way to reverse the process. Okay. So let's say we do this and it's successful and our algorithm makes sense. And given an image xt and the time step t, which it was noise at, we have a network that can predict back our noise. The problem is, how do we sample from this? Because before we wanted to approximate p with p theta, which is easy, right? because this gives us a distribution to sample from. This does not. Everyone see why that makes sense? So at inference time, our sampling algorithm just comes from right from what we learned. It makes sense? But the problem is it's not at all clear how we create a sampling algorithm with this new training objective. Turns out we still can. I'll come back to that slide later. And this is the sampling algorithm right here. I'm not going to explain this. It requires a lot of Gaussian linear algebra, but who remembers the trick I did before to show this was Gaussian? What rule do we apply? Bayes rule, okay. And what are the two terms in it that are Gaussian? Likelihood and prior, right. Well, it turns out that by applying Bayes rule, and like I said, you can do this more explicitly to show that a likelihood and prior in this specific case gives us reverse distribution that's Gaussian, instead of doing the easier way where you have this well-known fact that they already are. This actually just gives you more information than your reverse distribution being Gaussian. Doing some more algebra with this will actually give you a sampling algorithm for this. It's tricky. If you want to talk to me after about it, I can try to go through it and explain it. Again, we've burned through a lot in this presentation, so I would start in some other places first. That's why I decided to leave it out. But just take my word for it. With this approach, you guys will see that it's clear that if we solve this problem, we have a sampling algorithm. But if we have this problem, it's unclear how we have a sampling algorithm. It turns out that the authors in the DDPM paper, one of their main contributions is they showed that we actually do using this formulation. And for some reason, it works better in practice. Yeah? Okay. So now we're going to actually talk about a bit about how we predict back this noise vector. Because instead of having two neural networks that maybe parameterize our mean and our covariance matrix, we can actually, it's a bit easier to visualize with noise. That's why I left out the specific neural architecture for now. So how many of you are familiar with convolutional neural networks? Yeah, most of you? Okay. How many of you are familiar with autoencoders? Not in the variational inference sense, but just a neural network with a bottleneck. Sort of? Okay. So this is what an autoencoder is. Let's say for some other learning problem that doesn't relate to this, we have a 10-dimensional input and we have a 10-dimensional output. What we're going to do is we're going to create a bottleneck layer that's only vector with 5 dimensions in it. And our training objective is going to be to minimize the difference between our inputs and our outputs. What this allows us to do is it allows us to create nonlinear dimensionality reduction algorithms. So maybe if you're familiar with PCA, what is that? That's linear dimensionality reduction. Those are linear projections. In this case, we just want to learn a non-linear version of it. So you can think of it almost as like a generalization of PCA. Make sense? Okay, cool. Now, what's very tricky and what's interesting is sometimes we don't use this to just create these smaller latent representations of our image, but we use autoencoders actually just to create a tractable problem. So you can imagine with very high dimensional input, like a 512 by 512 image of a cat, your input to your model is going to be astronomically large. So the way we deal with this in classification problems originally would be a convolutional neural network or something like this. It turns out that we can use a convolutional neural network to create a smaller representation of our data and to feed it out into a larger network. So we're actually still going to have this bottleneck layer where in goes our noise, maybe our, not our noise, but in goes x of t and t. Out goes epsilon theta. And what we wish to is mean squared error between these. And the only reason why we have a bottleneck layer is just for computational tractability. Because if we have 512 times 512 dimensional layers for maybe a neural network with depth like 100 or something ridiculous like this, we just have too many models. We just have too many parameters in our model, and it becomes too big to train. So one just cheeky way to narrow it down is just create a bottleneck layer for absolutely no reason at all, because it makes the problem attractive. This is what a UNet does. I think it originally came from a biomedical imaging paper in 2017. Do you see how that drawing relates to this one right here? Kind of makes sense? Again, if this is confusing you at all, just think of your regular standard neural network. The only reason we do this is for tractability. Yeah? Okay. Another newer model to be able to do this that I think came out in 2022 is using something called a vision transformer. So who knows what a transformer is? Sort of. I'm not going to explain it. It's kind of complicated. We did a paper breakdown on it. So that's not my problem. But essentially what a transformer is you feed it in some input sequence. So you can imagine maybe this is a tokenized version of the English language in a sequence like, hi, my name is Alex. And the output you get is, well, I can speak German, but whatever, hi, my name is Alex, this is German, right? So it's a sequence to sequence model. Something that's very interesting is we can treat images as sequence. So if we have an image like this, we can actually, this is called raster sizing it, which is just a fancy way of saying, take a matrix and put it in a vector. And the way we might do this is split this part right here. So it goes into two pieces like this, and then just concatenate these pieces together to get this vector right here. Does this kind of make sense? So now you can see we have maybe a sequential representation of our image, pixel by pixel. Make sense? So we can use this transformer architecture plus some little tricks added to it to actually treat this, again, like we do with transformers, as a sequence-to-sequence problem. What's very interesting about this is, unlike our CNN or our UNet from before, where we're predicting epsilon theta, our CNN, because convolutions are linear, so you're not just stacking convolutions on top of each other, you're actually throwing in regular, fully connected neural network layers all in the middle of them. So your input needs to be of a fixed size. But with a transformer, instead, you can imagine maybe I have this 2x2 image like this, which again has this representation, but maybe I want to feed in a 3x3 image like this, which has this representation. So what's nicer is our transformer here is a bit harder to train, but you can see what it gives us instead is the ability to not only sample from 512 by 512 dimensional cat images, it allows us to sample from any kind of cat image we want. Any questions? Okay, cool. Now, well, I know it's kind of hard to follow, but does anyone know what's left? What's the one problem we haven't really solved? We've solved sampling from a distribution of cat images, but that's a fixed distribution that we train using only a data set of cats. We're not telling our model to generate an image of a cat and it's giving it a cat. Where maybe we want to tell our model to generate an image of a dog and it gives us a dog instead. We're not able to do that. We're only able to generate cats, right? So what else do we need to do?
Distributions to some tokens.
Exactly. So we need to condition on text. So if I input a sentence like, generate a picture of a cat underneath the sun with a picture of a dog in the background, a tree in the background or something. Because we want to be able to now condition our probability distribution on sequences at variable length. Does this make sense to everyone? Now, okay. So this is how you do it, which is this. I put this here because I think this is probably my expression when I first cracked open the paper and looked at the diagram, but it's actually not that hard. So what do we know so far, or kind of know, or kind of more familiar with? We know how regular diffusion works. So what we want to do is we want to be able to instead just slightly modify not even our algorithms, but just our neural network, and be able to inject some textual information into it. This makes sense to everyone. It's kind of obvious to everyone. To be able to condition on this, it doesn't really change any of our algorithms at all. We just want to input some extra conditioning information from into our neural network, and it should be able to learn this for us. Yeah. Okay, so the way you actually do this is you take a transformer and you cut it in half. You take an autoencoder, like we talked before, you cut it in half, and then you get your diffusion model out. Okay? And this is the simpler expression for what's going on. So here we have our diffusion model from before, right? We kind of understand this now. We give it x of t and t, and what do we get back? Anyone? This is our image and our time step. We get back our predicted noise, epsilon theta, right? Okay. So the first thing we're going to do is we're going to inject some information into, this is our neural network right here. And this is going to be some text input. Okay, that makes sense to everyone? Anyone know how to do this without like cheating and looking at the slide? Any ideas? Okay. Is anyone familiar with clip or heard of clip embeddings before? Okay. So I'm not going to talk about clip then, because this is just going to make this more confusing. But I'm going to talk about how we could be able to inject this information into our model. Well, it would use word embeddings at some point, but that's kind of besides the point. Well, what's one problem is our text representation. How many dimensions is it? We could do something weird where we could go like cat photo, and then we can call this pad, and we can call this pad. So now we say that, oh, we can represent any text conditioning that has either 0 words or 4 words. And we can take this as a 4-dimensional vector as input to our diffusion model, right? That's kind of janky though, because what if I want to type out a really long sentence and I don't have enough 4 words? Oh, well then maybe we want to make this 20 dimensions instead, but then you run into the same problem, right? Maybe these padding tokens cause some kind of weird dynamics during training where then when you make the vector very big and I want to just generate cat photos, it's paying so much attention to these pad tokens that something goes wrong or something like this. You can see why this is, it's a solution, but maybe not a great one, right? Okay. Here's what we can do instead. So again, to recap, what is our transformer doing? I give it a sequence, what does it give me back? A sequence. Okay, perfect. And what we want to do is we want to be able to turn this sequence into a vector. When I actually give my transformer a sequence, you might think, well, what is the dimension of each word, if you all had to guess? Maybe one-dimensional, maybe just a single number to represent one word. Turns out it's not the case, and we use these things called embeddings. And in the original transformer paper, this is actually a 512 dimensional vector. So we have a word and we have a 512 dimensional representation of it. So then what is the input to our transformer model now? Just to make sure it's on the same page. It's the same thing. It's still a sequence. It's just not a sequence of words. It's a sequence of 512 dimensional vectors. Does that make sense? Each vector represents this word. Okay, what is our output? Can anyone guess? It's still a sequence. A sequence of what?
Words, vectors.
Which are 512 dimensional vectors. Okay, I don't expect you to know, but just maybe that makes sense, right? Now, what we're going to do is maybe I want to. Okay, well, what's one way to take this to take a sequence of 512 dimensional vectors and turn it into a 512 dimensional vector? It's really simple. It's not exactly what goes on, because there's some different ways that work in practice, but there's a simple example. Yeah.
You add a zero vector? Wait, no.
What does that mean?
Oh,
So I
okay.
give you. Here's my problem. I give you a sequence of 512 dimensional vectors, and I want you to give me back a 512 dimensional vector. Think of any way to do it on your own. Sorry?
Yeah.
What do you mean transpose? So I give you maybe n vectors or 512 dimensional vectors, and you give me a single 512 dimensional vector back. It can be any way to do that you like.
Take the mean of each vector.
Yes. Or more simply, a bunch of vectors vi, and I just take the sum over I of vi. Right? Well, what's good about this is it's a linear function of our vi's, right? Is it differentiable? Yes. The sum of differentiable functions is differentiable, and this would just be maybe like the identity function, right? So what we can do is we can backpropagate. We can apply gradient descent. So now I'm going to have something where I give my model maybe W1 through Wn. What do I get back? Maybe I get something like V1 through Vn. And then I just take the sum from n to vi, and I get a 512 dimensional vector. That makes sense to everyone? Okay, very cool. This is essentially sort of how Clip works. And now what we can do is, well, what do we input to our model? Why did we do all this? Anyone guess? We implement the 500, we input this vector to it.
Someone here need help? Oh, sorry, you guys are
No, it's, yeah, not
lecture?
Lecture, we are doing a club event.
we're just,
Sorry,
it's okay.
How about?
So now we have some compact representation of our sequence of input words. So what do we condition our model on? This, right? It's a 512 dimensional vector. So we can augment the input to our diffusion model, or let's say we have a neural network right now that's maybe 112 at 512 dimensions because I shouldn't use the same number, it might be more confusing to you, but we have our input x of t, right? And maybe I just want to extend network by 512 dimensions to give it this conditioning vector or this conditioning information, or this 512 dimensional vector that represents my sequence of words. Okay? And that's going to be my model now. So what happened to the presentation?
It's just like subword.
Oh, okay. Well,
Maybe it shows on the side.
yeah. So
I was trying to like correct it again, but it just
maybe you guys can.
you use it with the direction switch to the past.
Huh? No. Again, let's not worry about that. Can people see? People see this diagram from before reasonably well. I got a big screen, so it's good. These key query value matrices that look kind of scary from before are actually key query value matrices, which are parts of our transform. And whenever you see these key V matrices right here, you can think of all that is this yellow part right here is just our 512 dimensional vector. Okay. Now we have one more problem to solve, is dimensionality. Sometimes this thing gets very big, and if we tack on another 512 dimensional vector onto it, maybe it gets too big or something like this. So remember our trick from before with our autoencoder that gives us a lower dimensional representation of what we're working with. Here's what's very cool is I'm going to actually place my diffusion model here, call it DM, my decoder here. So as input, I give it, again, x of t and t. It gives me some lower dimensional representation of x of t and t. I pass this to my diffusion model. I pass the latent or lower dimensional representation of my noise vector back to the decoder portion of this encoder. And that's what I call epsilon. Turns out in practice, it's very hard to train a decoder and an encoder and a decoder at the same time as we're training our diffusion model. It leads to, it's just difficult to train. It's kind of hard to understand without some extra information. So this is actually just a pre-trained model or a pre-trained image encoder. So we have some model that gives us these smaller representations of images that is already a trained model. And what we do is we pass in a true image in this, perform our entire diffusion process in this latent space, and then map it back. And it turns out this works quite well. And it allows us to not deal with dimensionality things, not deal with training this encoder and this decoder. And it allows us to perform our entire diffusion process in this, what we call a latent space or a lower dimensional space. Of course, on top of this, we have our text sequence that we also give as input to our diffusion. And you saw how we can take this sequence-to-sequence model, create a vector out of it, and pass this to our diffusion model. Of course, this vector is very arbitrary. If we take a pre-trained sequence-to-sequence model, we expect it to perform kind of well. Like if I give it a sentence in English and it's supposed to give me a sentence in German, if it's a good model, it does give me my sentence back, but translated to German. But the problem is when we take a summation over all of our vector representations of our words, this is not guaranteed to have semantic meaning, right? It's completely arbitrary. Maybe it's possible that it somehow could, but we don't expect it to, right? So unlike where this is pre-trained, you actually take a pre-trained text encoder And even though you perform this summation, which might not have any real semantic meaning, in order to give it semantic meaning, you need to backpropagate your gradients through this. So you backpropagate through your diffusion model, backpropagate through your text encoder, but you don't touch your encoder, decoder for your image whatsoever. Kind of makes sense? Okay, so that's it. I think we're done.
One question. In the diffusion, the original, when you're adding noise, I'm assuming it's on a full dimensional image.
Yes.
So how does it work if it's in using lower dimensional space?
Right. So I'll just go over this point one more time in case anyone's confused.
Or are you accessing a sort of a
So
component or some
Let's-
other?
let's think of this
Step
in
in
a
that.
different problem domain. Let's say, I know this comes up in engineering sometimes, and maybe, I don't mean to push it on the spot, but you've seen dimensionality reduction in civil engineering. Maybe we have some vector that describes some engineering process that's going on, but it's very, very big. Maybe it's 1,000 whatever data points, so it's 1,000 dimensional vector. And I want to extract some important information from this, or the most important 8 data points from this. So one way to do that is using PCA. So we can train a model that gives us, okay, I'm not going to draw out 8 things, so now it's 4. So we train a model, a linear model, to linearly project this vector onto this lower dimensional space, and then project it back to a higher dimensional space, and we just minimize the mean squared error between these 2 things. And you can do this analytically with PCA. You don't need to actually do this using gradient descent. You can just do it using, like, I think singular value decomposition is enough. It's actually just an eigenvalue problem. And what you get back is you get back your 4 vectors that mean the most. Maybe not the exact values of them, but you're able to invert and look where these values actually came from in your original thing. So it might tell you the things with the most meaning in them, or the things that you should care about. Okay. Now what we do is we generalize the problem, where instead of caring about having an explanation for 4 things in this part that matter, what we actually have is we just want what's called a latent or lower dimensional representation of what we're working with. So we map here, but it's no longer linear. We map here using a neural network, maybe just a single layer fully connected neural network to map from 1,000 dimensions to 4. And we train this using gradient descent to minimize the difference between these 2 things right here. Now, what we do is, this is very nice because we can say perform operations or do other things with this smaller representation of our data. After we do those things, we can map it back to the higher dimensional representation. And it turns out this works very well. You can do this using standard autoencoders because there's no guarantee that maybe if I have 2 vectors as input to this model, I add them, maybe I add the vectors together, I pass them through here, I pass them back, and I get the same thing. There's no guarantee that operations in this lower dimensional space are the same as operations in this higher dimensional space. They almost always aren't because this is a nonlinear mapping, right? So instead we use these things called variational autoencoders, which are another kind of generative model, which allows us to do things like treat operations like addition or multiplication in this space as maybe addition or multiplication in this space, which is very nice because what it allows us to do in the case of diffusion is encode our image to the smaller dimensional space, perform diffusion in the space using maybe operations such as this, decode back to our higher dimensional space, and everything works out.
So this is at the beginning. There is you are, like, when you're training the diffusion, it is on a lower dimension. It understands
All of the
lower
training
dimensional
is in this space.
Yeah.
You're not training this whatsoever. All of this is pre-trained.
No, the original, you get the original sort of, when you started it, it gives the impression that it's using full dimensional images, but they do get lowered in that
Yes.
stage as well.
The only reason we do this is just for tractability, because we will need to have many more parameters in our diffusion model if we're dealing with things with this dimension instead of this dimension. Of course, there's trade-offs to this, because maybe this diffusion model becomes less expressive, or maybe this lower dimensional representation of this loses too much information. So it's an interesting trade-off where you'll have to try out, these are called autoencoders of maybe different sizes. So maybe this needs to be a little bit bigger than it actually is. So you need to take another pre-trained model to work it with. You kind of just need to go off and do this on brute force and tell on your own and look at how training is going while you're training this diffusion model and see whether or not this isn't too small, but it's also not too big, because too big, too many parameters, too small, we lose too much heat from our original function. Yeah. And then, of course, like I said before, in the middle of here, you have a text encoder, which, okay, I should change this because I said this big circle is for just what we backpropagate on. Our text encoder is a part of that. That make sense? Okay, cool. I know it's a lot, but maybe you guys kind of understand diffusion a bit better, or want to do it together. Yeah, good question.
Yeah. I heard this term, like, are diffusion models explainable? Like,
This is a very hard problem. I'm actually working on this.
oh,
So I'm probably going to drone on for too long, and this presentation's gone on for far too long. Thanks everyone for staying. I don't even. Oh god, yeah, we went like half an hour over, so I'll talk to you about that after, or anyone else wants. But thanks so much.